In this video lecture, we will see how to measure electrolytic conductance, specific conductivity, equivalent conductivity and molar conductivity. And before this video lecture, we have already gone through all these concepts, right? Now we'll see how to measure it experimentally, right? And before we go ahead and deep dive into this, let's just recall some of the basic concepts that we have already learned in physics, right? We know that if this is a rod, this is a conducting rod of length L, area of cross section A, right? And if I pass current through this battery into this metallic wire, then when the current will start flowing in this metallic wire, there is an obstruction that is offered to the flow of current, right? And we know that obstruction is known as resistance, right? Resistance offered or obstruction offered to the flow of electric current, right? So current is flowing, right? And resistance denoted by R is obstruction offered in the flow of current denoted by I. Now just understand this here. In this case, when we are saying that we are passing electric current through a metallic wire, right, at the same time it is also able to conduct electricity. When we are talking about, or when we are studying electric current, right, in terms of resistance, right, so at the same time it's also able to conduct current, right? So we have resistance which is trying to stop the flow of current. At the same time it is also able to conduct electric current, right, which is known as conductance. So resistance and conductance, we say, are reciprocal of one another, because conductance is flow of current, right, or the current that is being conducted by the conductor, and resistance is obstruction to the flow of current, right? So resistance is trying to stop the flow of current. So we say resistance is reciprocal of conductance. Conductance denoted by C, or somewhere you also see in chemistry it's denoted by G, right? So there is a formula that is derived for resistance. We say that resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section. Directly proportional to L, length of the wire, and inversely proportional to the area of cross section, thickness of the wire. And if I remove this proportionality sign, I'll put a constant A. This constant is resistivity. This constant is resistivity. So we can write it as resistivity is equals to R A upon L, right? This is the formula for resistivity. Right. So here we are talking, or we are discussing this flow of current in terms of resistance. Now let's just see what is conductance. Since we said that resistance is reciprocal of conductance, that means conductance is equals to 1 upon R, right? So here conductance would be, if I put the value of R from here, it would be 1 upon rho A upon L. So like resistance is reciprocal of conductance, similarly this resistivity is reciprocal of conductivity, right? Resistivity rho is reciprocal of conductivity, denoted by this kappa. So here, instead of 1 upon rho is equals to 1 upon this. 1 upon rho is equals to kappa, which is conductivity. So instead of 1 upon rho, I can write it as this conductivity A upon L, So we have conductance is equals to rho A upon L, right? So this was in case of metallic conductors, and we already know all this from physics, right? So we will be using the same concepts here in chemistry while studying conductance through electrolytic solutions. This is Wheatstone Bridge. We have done this in physics. So as per the principle of Wheatstone Bridge, or let's just see what it is. There are four resistors which are connected in the form of parallelogram, right? And in the one diagonal of this parallelogram we have galvanometer, and to the other diagonal a battery is connected, right? So you pass direct current through this battery, right? And we will arrange these resistance, right, all these four resistances in such a way that when current is passed through this battery, this galvanometer will not show any deflection, because galvanometer will show deflection when current will pass through it, right? So since we studied here that resistance is the obstruction that is in the flow of current, right? So if we arrange these resistances in such a way that no current will flow through this galvanometer, at that point this Wheatstone bridge is said to be balanced, right? So I'll repeat, we will arrange these resistances in such a way that when direct current is passed through this battery, this galvanometer will not show any deflection. On passing current through this battery, this galvanometer will not show any deflection. That means no current is flowing through this galvanometer when the Wheatstone bridge is balanced, right? So we say when bridge. Why do we say it as bridge? Because these are arranged as bridge. R1, R2, it's kind of a bridge, right? When bridge is balanced, no current flows through galvanometer G, right? So at that point when no current flows through galvanometer, we have ratio of R1 upon R2 is equals to R3 upon R4, right? So if we know the ratio of R1 and R2 and one resistance say R4 or R3, then the other unknown resistance can be calculated. I'll repeat, if we know R1, the ratio of R1 and R2, and say we know R4, then R3 can be calculated, the unknown resistance. And just in case, this R1 is your variable resistance, this is your unknown resistance, right? So if you know R3 upon R4, right, R1 is variable resistance, one of the resistance can be calculated if you know the ratio of R1 upon R2, and say you know R4, so R3 can be calculated, right? So this is the introduction to your Wheatstone bridge. Now we'll apply all these concepts here in the conductance of electrolytic solutions, right? So if you look, since we are trying to calculate the resistance, the resistance or conductance of electrolytic solutions, right? So if I know resistance, right, then as per this relation I can calculate the conductance, right? So this is one way, right, this Wheatstone bridge. If I somehow take this solution into this Wheatstone bridge, right, if I make this electrolytic solution as one of the resistance in Wheatstone bridge, then I can calculate that unknown resistance of this electrolytic solution. Say, suppose if I know R1 and R2, right, and I know R4, right, then in place of R3, if I put this electrolytic solution, right, then the value of that R3, which is this electrolytic solution, can be easily calculated. And once we know the value of resistance, we can calculate conductance, right? But But the problem is that we cannot connect this electrolytic solution to the Wheatstone bridge, right? Because this is not a wire. This is a complete, because if you want to calculate the resistance or conductance of electrolyte, if of an electrolyte, then you need to take it in a solution, right? So I cannot connect a solution of an electrolyte in the Wheatstone bridge, right? This is one of the problem, right? So this problem is resolved, right, using a device known as conductivity cell, right? This conductivity cell contains the solution of an electrolyte between the two electrodes. These are the two electrodes, right? So between these electrodes we have the solution of an electrolyte, and we need to calculate conductance for that electrolytic solution, right? So the first problem was this electrolyte or electrolytic solution cannot be connected to Wheatstone bridge. Right? So this problem, right, is resolved by this is resolved by taking conductivity cell. Right? And we place this conductivity cell in this thermostat. This is a thermostat, right? This thermostat will maintain the temperature of this conductivity cell at constant, right? So this will keep the temperature constant for this electrolytic cell, right? Now, the second problem is, or the second thing is, like here, when I reached at this relation, this R1 upon R2, R3 upon R4, so I passed direct current, right? And then I arranged these resistances in such a way that no current flows through this point B and D, right? That is, and this galvanometer will not show any deflection since no current is passed through B and D. And I have arranged these resistances such that no current will pass through this galvanometer, which is in this between this point B and D, right? So here, since here I'm passing this direct current through this battery, right? Let's see what happens if I pass direct current into this electrolytic cell or into this conductivity cell. We know from electrolysis, or when we did conduction through electrolytes, how current is conducted through electrolytes. If you remember, we to the electrolytic cell or to voltmeter, we have connected a battery and we passed electric current, direct current through that battery, and that when we passed that direct current, the ions will start moving towards opposite electrodes, right? And due to the movement of those ions, that electrolytic cell or that electrolyte will start conducting electricity, right? So on passing direct current, electrolysis will start, right? But here, if you look in this situation, we are trying to find the conductance of this electrolytic cell. We are trying to find the conductance of this electrolyte, right? Or we are trying to find the resistance of this electrolyte. So if I pass electric current, say if I pass direct electric current like I am passing here, then that electric current, direct electric current, will cause electrolysis, right, in this conductivity cell. And when it will cause electrolysis, that means ions will start moving away from these electrodes, right? So when ions will start moving away from the electrodes, we know that when ions will start moving towards opposite electrodes, the change in the concentration of ions will take place, right? and the conductance or the conductivity of electrolytic solutions depend on the ions, on the number of ions, right? Since there would be change in the number of ions, when ions will migrate towards electrodes, they will discharge at the electrodes, right? So that will result into the change in the number of ions. So changing number of ions means resistance will get changed and conductance will also get changed, right? So this is the big problem. So what we will do, I'll write it over here first. DC current, direct current will cause electrolysis to start, right, in conductivity cell, right, which will change resistance due to change in the number of ions, or we say ions will start moving away from the electrodes and there would be change in the concentration of ions near the electrodes, right? So when the number of ions will change, resistance will change and conductance will change. So it would not be possible to find the conductance or resistance at one point of time, right, since ions are moving on passing direct current. So this problem is resolved by taking alternating current instead of direct current, right? So if I take alternating current here, then in one phase, we know in alternating current what happens. In one phase current will flow, it's like this. In one phase current will flow, then current will flow like this, then the current will flow this, then this. In one phase, say in this phase, current will flow, so then in this phase current will not flow, right? So the electrolysis, if caused or if there is any change in this phase, that would be reversed by the opposite phase, right? So we use alternating current instead of direct current in this experiment to calculate electrolytic conductance, right? So we say we use alternating current instead of direct current, right? So alternating current of 550 to 5000 cycles per second, alternating current of this much frequency, alternating current of audible range. This is your audible range, right? Audible range, right? So this problem is resolved. The problem of direct current that could cause electrolysis is resolved by taking alternating current, right? Now again there is a problem. I have galvanometer here, right? So I cannot use galvanometer with alternating current, right? So instead of galvanometer, we would be using headphone, right? The normal headphones that we use to listen to the music, right? So galvanometer cannot be used with alternating current, so we use headphone, right? So here we are determining the null point using galvanometer. So here in this experiment we will determine null point using headphone, right? We'll see that in just a moment, right? So this problem is resolved. The problem of direct current is resolved by using alternating current, and with alternating current, since we cannot use galvanometer, so we will use headphone, right? And using the headphone we will determine the null point in this experiment, right? And this effect that is caused by this electrolysis, right? These effects are known as polarization effects, right? So we have something called as polarization effects here. I'll just write it over here. These are polarization effects caused by direct current electrolysis, right? And here in these electrodes are platinized platinum electrodes. That means platinum electrodes of platinum coated with platinum black, right? When electrodes of platinum are coated with platinum black, we call them as platinized platinum electrodes, right? And why is it is coated with platinum black? Platinum electrode is coated with platinum black. Why? Because we know that platinum can absorb some gases like hydrogen and other gases, right? So when in one phase, when there is a direct current, when there is a current in one phase, suppose if there is any gas due to electrolysis, suppose if there is any gas, then that gas would be absorbed by this platinum black, right? So platinum black will absorb any gas formed due to electrolysis, right? So any gas, if formed, would be absorbed by this platinum black, which is coated on platinum electrode. This is simple. And there is one more use of this platinum electrodes that are coated with platinum black, is that it increases the sensitivity of the headphone. That means the minimum sound that is used to determine the null point would be sensitized, right? So this is it. So these are the three important things, or these are the three important replacements or adjustments, that we need to do in Wheatstone Bridge to measure the electrolytic conductance of electrolyte. The first was we could not make this electrolytic solution as one of the resistances. Since this electrolytic solution cannot be made as one of the resistances, so we cannot use this Wheatstone Bridge, right? So what we will, and we cannot, this principle would not be applied, right, of Wheatstone Bridge. So what we did in the principle of Wheatstone Bridge, what we did, we, instead of using resistance, what we did, we used this conductivity cell that has electrolyte between the electrodes. Second is, we cannot use this battery, right, because battery is a source of direct current. So we cannot use direct current, because direct current will cause the electrolysis of the electrolyte. And when this electrolyte will undergo electrolysis, then the ions concentration will change. That will result into the change in resistance of the electrolyte, and in a way it will change the conductance. So conductance or resistance at one point cannot be calculated if we use direct current. And then instead of direct current, now we are using alternating current of frequency, of audible frequency 550 to 500 cycles per second, right? And since we cannot use galvanometer with alternating current, so we replace this galvanometer with headphone, right? And we will coat the platinum electrodes with platinum black, right? Why? Because if there is any gas produced due to electrolysis, it will get absorbed on the platinum black, right? So this is the total changes that we have done in, or the adjustments that we have done in Wheatstone Bridge. Now let's look at this experiment. As per this, what we do is, if you look at this arrangement, this is the source of alternating current that we have discussed, right? And this is a sliding jockey experiment. You might have seen this in the physics lab, or might have done this in the physics lab probably, right? So we have arranged these resistances, right? These resistances between A and C, right? These are resistances, and this is the resistance we have taken. This R is the resistance we have taken from resistance box, right? So what we do is we will slide this jockey on this wire, right? And we will listen to the headphone, right? The point when we are sliding this jockey on this wire, the point at which we hear minimum sound in this headphone, that point is known as null point, right? And if we apply the same Wheatstone bridge principle at null point, the resistance at null point when minimum current or no current is flowing through this headphone, right, then at that point the the potential difference between point D, the potential difference between point, say between this point and this point, say this is E point, between point this and this, between which this headphone is connected, it is connected between these two resistances. One is the resistance of this wire, and then we have this resistance. There is a wire connected, similar to this arrangement. If you see here, this headphone, this galvanometer, is replaced with headphone, like here, and there are two wires, this and this, right, which is connected between these 2 points. Similarly, and there are resistances across this point. Similarly, this headphone is connected between point D and point E, and at the null point, right, when this jockey will move to a point, say point D, where we have null point, there is minimum current or no current in this headphone, right? And you will see the the null point is determined when there is minimum voice in this headphone, right? So at that point, when there is minimum voice, we say that this AD, okay, before this X is the resistance of this electrolyte, right? If you see this, the electrodes are connected between to these metals, right, which are of specific resistance. So the resistance, this X is the resistance of this electrolyte, and we have to find X, right? Say I move to take this jockey to point D, right, and here it is a null point, right? So at null point, resistance E, resistance R upon resistance X, right, resistance R upon resistance X is equals to AD upon DC. This is as per this formula. If you remember, R, resistance, is directly proportional to length, right? At null point, I write it over here, at null point, when there is minimum voice in headphone, right, when there is minimum voice in headphone and there is no current or less current flowing through this headphone, and we have potential between these points as potential difference between these 2 points as 0, right, or we say the potential is same between these 2 points, right? So at null point there is minimum voice in the headphone, and at null point, when there is minimum voice, right, at that point this bridge is, or this arrangement is balanced, like it is balanced here in Wheatstone Bridge, right? So at null point we have this is a known resistance. This is taken from a resistance box, standard resistance box, right? This is X, which is the resistance of this electrolyte, right? So let's say this jockey is at point D, so we write it as resistance R upon this. Resistance X is equals to AD, right, upon CD, right, this upon this. Length, this is length, AD upon CD, right? So once you know since you know the